Hello students, welcome to EPG Pathshala. I am Dr. Imtiaz Hassan from Jamia Millia Islamia, a Central University. Today we are going to talk on the module IR spectra of functional groups, IR bands of peptide and proteins under the paper Techniques used in molecular biophysics part 2. After studying this module, a student will be able to understand IR spectrum. What is the significance of IR spectrum? What kind of information we can derive from the IR spectrum, and how the IR spectrum used to identify the different types of molecules or chemical signatures. Then we talk about the regions of the IR spectrum. There are 4 regions of the IR spectrum, so we will describe importance of each region in detail. And then we talk about what are the factors that affecting the IR bands in detail, because you must know that the IR spectroscopy depends upon apart from its bonding nature of the bonding, it's also dependent on the environment of the chemical bond. That's what we should see, the effects of the environment on the bind pattern. And then IR spectra of various functional group will be described in detail, like the alkane, alkene, alkyne, alcohol, amine, ester, like that. And finally, I will discuss about detailed information about the IR spectra of the biological molecules such as protein, carbohydrate, vitamin, fats, fatty acids, lipids, etc. Now we talk about the IR spectrum. So the IR spectrum is actually the vibrational spectrum of a molecule, is considered to be a unique physical property and is characteristic of the molecule. IR spectroscopy measures the bond vibration frequencies in a molecule and is used to determine the functional group mainly. And based on that functional group, you will be easily able to identify the chemical properties and what are the actual chemical compounds or trace material as well. The infrared spectroscopy can be used as a fingerprint for the identification of unknown compounds. It also gives you the information about the structural feature of a molecule or the functional group attached to a molecule, which produces a characteristic and reproducible absorption spectrum in the IR region that can be used to analyze, or you can identify the different types of molecule and its structural and functional properties. This technique is widely applied in the analysis of organic materials. It is also used for the polyatomic inorganic molecules and for the organometallic compounds in the different types of IR region. There are 2 sections of IR spectra: the functional group region, which lies in the greater than the frequency of 1500, and the fingerprint region, which lies in the frequency less than 1500 wave number. We discuss here that what kind of chemical structure give you the IR spectra, like which compound is IR active and which compound is IR inactive, or you can say what are the major requirement for the compound to be IR active. So there is only having the simple 2 criteria. A polar bond is usually IR active, and a non-polar bond in asymmetric molecule will also observe weakly but not at all. For example, you can see here, it's shown in a spring model, that if the 2 forces, positive and negative force, acting in an opposite direction, then the molecule are compressed and its dipole moment decreases. If the 2 charges are having forces on opposite direction, then molecule is stressed and dipole moment increased, and that's what the electric field increase, and you'll get the more signal and the stretching occurs. The IR spectrum. The IR spectrum measures actually how much and what frequency of light is being absorbed by a bond vibrations, in which the y-axis indicates in the form of either percent transmittance. At 100% there is no light absorbed, and that wave number, and 0% means all light are absorbed. In other way around, it is also presented in the logarithmic form, in the form of absorption. If it is present in the form of absorption, then the peak obtained as an upright peak. However, if it is present in the form of transmittant, then the peak is obtained as a downward peaks. But both are equal in magnitude but opposite in the direction. However, at the x-axis indicates either frequency or wave number, but generally wave number is used for the convenience. And each peak correspond to the particular bond, and peak are above 1500 centimeter indicates the properties of functional group, and lower 1500 gives the information about the fingerprint region, which can help you to exactly identify the chemical properties of the particular compound which are under investigation. We discuss here what are the regions of frequencies and what kind of information you derive from in the each region. So IR spectroscopy is generally divided into three distinct regions. One is the near R region, which having the combination bands. It may frequency range from 3.8 into 10 to the power 14 to 1.2 into 10 to the power 14, and its wave number is 12,800 to 4,000, and wavelength ranges from 0.78 to 2.5 micrometer. The mid-IR region, it gives the fundamental bands for organic molecules, and its frequency lies in between 1.2 into 10 to the 14 to 6 into 10 to the power 17, and its wave number is corresponding to 4,000 to 200 per centimeter, and its wavelength is 2.5 to 50 micrometer. And the third one is the far IR, which is applied for the inorganic and organometallic compounds, and it's having frequency in the range of 6 into 10 to the power 12 to 3 into 10 to the power 11, and wave number is ranges from 200 to 10, and its wavelength is 50 to 1000 micrometer. We discuss about what does the absorption intensity depend on. The intensity of absorption depends on how efficiently the energy of an electromagnetic wave of frequency mu can be transformed to the atoms involved in the vibration. You can see here in a figure a dipole is generated and it exerted the electric field. The greater the change in dipole moment during a vibration, higher the intensity of absorption of a photon. So the dipole moment must change during a vibration to be IR active. In order to interact strongly with the electromagnetic radiation, the motion of the molecule must be such that the dipole moment changes. In order to absorb infrared radiation, a molecular vibration must cause a change in the dipole moment of a molecule. So these are the following essential criteria for a molecule IR active and gives an IR spectrum. Now we talk about the key functional groups by region of the IR spectrum. The two factor influences the energy and thus the wave number at which the bond absorbs. The IR bond strength and the atomic masses. These two properties, like what are the types of bond, double bond, single bond, triple bond, and of course it decides the strength of the bond, and atomic masses, because higher masses is actually determines the vibrational state of the molecule like an spring. The stronger the bond vibrates at high frequency, and similarly the lighter atom vibrates at higher frequency. So the lighter atom means the molecule with the low molecular mass, atoms with the low molecular mass with having very high frequency. However, the molecules with the higher masses having the low frequency. Similarly, a single bond to hydrogen are weaker than the double bond or triple bond. Like you can see, the single bond are the weaker in nature as compared to double and triple bond, but the atomic weight is much lighter in these bonds, which creates a higher frequency of the bond vibration. That's what the despite of bond low, a single bond in the hydrogen atoms, because of their mass are very low, it gives the very high frequency. We discuss how we analyze the IR spectra and how you gain the information from an IR spectrum. So these are the fundamental points which has to be remembered, that the primary use of IR spectrometer is to detect functional group. Simply, it is to detect the functional group. Since most types of bond in covalent molecule have roughly the same energy, that is the CC double bond, carbon oxygen double bond, carbon hydrogen single bond, and carbon nitrogen hydrogen single bond, they show up in the similar region of the IR spectrum. Remember, all organic functional groups are made of multiple bonds and therefore show up as multiple IR bands. So the whole IR spectrum is divided into four principal regions, with the first one is giving you information about the hydrogen like OH single bond, NH single bond, and CH single bond, and in a region of 4000 to 2700 per centimeter wave number. The second region gives you information about triple bond like the carbon-carbon triple bond, carbon-nitrogen triple bond, and it lies between 2700 to 2000 per centimeter. And the third region gives you information about double bond like carbon-oxygen double bond, carbon-nitrogen double bond, carbon-carbon double bond, and it lies between 2000 to 1600 centimeter. And the fourth is the most important region, that is lies between 1600 to 400 per centimeter, and it gives you information about the single bond like carbon-carbon, carbon-nitrogen, carbon-oxygen, and this region is known as fingerprint region, with having the actual signature of any molecule. Now we talk about the key functional group by the region of the IR spectrum. The energy of photon in the IR region correspond to the difference in the vibrational energy level within the molecule. The vibrational energy level are dependent on the types of bond and bond strength. As I discussed already, that the type of bond means double bond, triple bond, and single bond, and of course the bond number decides the strength of the bond, and it also depends upon the group attached to them. The IR is highly useful to determine if the certain type of bond or functional group are present in a molecule. Now we talk about the factors which affecting the IR bonds. The intensity of an IR bond is affected by primarily two factors. First, whether the vibration is one of the stretching or bending, and electronegativity difference of the atom involved in the bond. Because, for example, if the two bonds are held together, then the attached atom, which is high electronegative, then it induces the more dipole moment. Then it is if it is the stretching or if it is the bending, that is also decided by the attached atom, and the pole difference in the dipole generated is also decided by the types of vibration, whether it is stretching and bending, and of course the number of types of atom attached. And for both the effect, the greater the change in dipole moment in a given vibration or bend, a larger the peak intensity was observed. And the greater the difference in the electronegativity between the atoms involved in the bonding, a larger the dipole moment occurs. Because greater the difference in the electronegativity, both the two atoms are induces more dipole, because our electrons are migrated towards the highly electronegative atom, and so that one side got slightly positively charged, more positive charge, and the other group got the more negative charge, so induces a very good dipole as the electronegativity increases. Typically, stretching will changes the dipole moment more than bending. So this point must be remembered, that the stretching vibration produces more dipole moment as compared to the bending moment, because it increases the distance of the atoms. Now it is important to make note that the peak intensity show the effect of these factors. These factors are actually for decides the peak intensity. For example, a strong peak is tall when transmittance is low. Medium peak is mid of the height, and weak peak is short and transmittance is the high. Broader peak if the Gaussian distribution is abnormally broad, and this is more for describing a bond that spans many energy. The exact transmittance value are rarely recorded. From the molecular point of view, discounting phase, temperature, and other experimental conditions, there are factors that contribute to position, intensity, and appearance of IR bonds. The mechanical coupling that produce the constitutional isomerism. The Fermi resonance is because of stereoisomerism. Hydrogen bonding is of the symmetry. Ring strain gives the conformational isomerism, and electronic effects because of the tautomerism or the dynamic isomerism. So the position of the spectral band is dependent on the bond strength and atomic size, and the intensity of the peak results from the efficiency of the coupling. For example, vibration that have a large change in the dipole moment creates a larger electric field with which photon can couple more efficiently and thus produces more intense bands in the IR region. We discuss what are the factors affecting the IR bonds. It is a very important slide. Here you find that a simple equation gives you the idea. You can easily understand what are the features that decides the intensity of IR spectrum. It is given as the frequency equals to 1 by 2 pi c into root under k by mu, where c is the constant and k is the another constant. So larger the k, higher the frequency, and mu is the larger the atomic masses, lower the frequency. So this relation you have to remember, that if the constant value is low, frequency is high. If the mass is the low, frequency value is the high. If the larger the k, the frequency is high. So you can see here in first case that the carbon-carbon triple bond, carbon-carbon double bond, and carbon-carbon single bond. So as the k value increases for the triple bond, so the frequency and intensity is increasing from single bond to triple bond. In the other case, you can see that as you increase the mu, that is the mass, the decrease in frequency. For example, carbon, if carbon is attached to hydrogen, if carbon is attached to carbon, if carbon is attached to oxygen, if carbon is attached to chlorine and bromine, as we increase the mass, a decrease in the frequency was observed. For example, here you can see that the hydrogen bonding increases the frequency. Like you can see that if it molecule is hydrogen bonding decreases the frequency. As you can see here that if it is the hydrogen bond is available, then it having the 1680 per centimeter, but if there is no hydrogen bond, its frequency decreases. Now we took the example of other group like alkene factor influencing the vibrational frequency. For example, a strain move peak to right decreases. For example, if you have the bigger alkene, bigger cyclic compound having the 7 carbon, it having the frequency of 1650, but if it is the 4 carbon, it is having 1566, and with an exception that if it is having 3 carbon, then it having 1656 as an exception because of the angle formation. Then again with the substitution, there is no substitution and it is mono substitution and it is a dice substitution. As we increase the substitution, frequency increases. You can see in many examples. And conjugation decreases the frequency. As we increase the conjugation, the frequency, a decrease in frequency is observed. Here we discuss about the group frequencies and its analysis. You can see here the example of alkane, what kind of IR spectra of alkane we get. So alkane, due to the small electronegativity difference between carbon and hydrogen, hydrocarbon bonds are of medium intensity and best give intensity at best and give a simple spectra. You can see the spectra of dodecane and cyclopentane, almost similar kind of spectra, and it gives CH bond intensity for the methylene band around 1465 per centimeter, for the methyl group at the 1375, and CH2 group it having the 720, and carbon-carbon single bond, no interplay is useful for the small tweak peak. So you can see 4 different peaks are for the alkane. We further discuss about the alkanes that additional if 1400 to 1350 region is free of interference the presence of certain alkyl group can be descended. For example, methylene and methyl group, because of the scissoring in the methylene group having frequency of 1465, and for the methyl group bending in the asymmetric giving the 1450, but the bending at the symmetric it giving a 375. So you can see here the additional thing also influences the frequency of the IR spectrum. We discuss about the IR spectra of the alkene. You can see here typical IR spectra of 8 carbon containing alkene likes 1 octene, and alkene in the trans 4 octene. So both having slightly different spectra. You can see in the table that the carbon hydrogen single bond gives the stretching vibration around 3095 to 3010. That's diagnostic for the unsaturation, may be aromatic as well. And CH frequency out of the plane in the form of bending is give the frequency of 1000 to 650 and can be used to determine degree of substitution. And carbon-carbon double bond is giving the stretching vibration at a frequency of 1660 to 1600, can be reduced by the resonance, and symmetrical carbon-carbon do not absorb, however the trans weaker than cis. In the endocyclic ring, strains shift the carbon-carbon double bond to lower frequency, example cyclopropene. You can see here the 7 carbon atom to the 3 carbon atom, the frequency is increasing continuously, however only the 3 carbon atom with an exception that having a frequency of 1656 nanometer. Gives the spectrum of alkynes. You can see the spectrum of 3 hexane and 1 hexane, and the information about it can be symmetric, pseudo-symmetric or internal symmetric, greatly reducing the number of observed bonds. Carbon hydrogen at 3300 stretching vibration are diagnostic for the terminal alkyne. Carbon-carbon triple bond at 2150 is stretching vibration and can be reduced by the resonance. Asymmetric and pseudo-symmetric carbon-carbon triple bond do not absorb, and carbon hydrogen around 900 to 700 bending, possible not to observe any bands for the carbon-carbon system. We discuss about the IR spectrum of amines. Amines are of different types, for example primary amine, secondary amine, tertiary amine. For the primary amine you will get the peak intensity at a frequency of 3500 33 centimeter for the doublet, and frequency without hydrogen bond affecting NH stretching. For the 1600 centimeter you will get the NH scissoring, a broad intensity at 700 900 to 900, NH2 wagging, that is the broad and strong, and 1080 per centimeter carbon nitrogen structure, weak for the alkyl, and 1300 per centimeter aromatic nitrogen strong bond. For the secondary amine 3400 per centimeter for the singlet structure and weak carbon nitrogen at 1125 centimeter. For the tertiary amine, no good IR band, adjacent to CH2 will shift 2800 per centimeter, and a tertiary amine salt NH bond at 2500 per centimeter is observed. Amine salt are NH3 plus like methyl, but broad NH structure centered at 3000, broad deformation at 1520 to 1570, and RNH R2 NH2 plus 300 broad spikes at 2200 2500 per centimeter, NH2 scissor at 1600 per centimeter broad. We discuss about the IR spectra of alcohol. You can see the IR spectra of phenyl ethanol, 1 phenyl ethanol and 2 piperidinial ethanol, and these are the quite different. COH is stretching at 3600 per centimeter in dilute solution, typically hydrogen bonding at a lower frequency around 3400 centimeter, and carbon oxygen stretching in the same region as CC but not much more intense. Positive position is sensitive to substitution pattern, or for example CH2OH for the primary alcohol it is the 1050 per centimeter, but it is the iso alcohol it is the 1110 per centimeter, and the tertiary carbon, it is giving the 1175 per centimeter. We discuss about the different functional group, like for the ester, you get the peak at the 1800, 1750 centimeter. For the ROCl group, you get the 1800 doublet peak. Fermi resonance, analogous to carboxylate ion, strong bonds at nitro group. Aromatic nitro 1520 and 1350 per centimeter, and aliphatic nitro 1550 and 1370 per centimeter. Ketones also having a good peak at, if it is the associated with the hexadene, cyclohexane, that giving the 1715 per centimeter, but cyclopentene 750, but cyclobutane it is giving 1780. Ketone is also very sensitive to conjugation. Intensity observed at 1660 to 1700. If it is aromatic substituted, then it is the 1650 to 1700. And if it is the hydrogen bond formation occurs, then it is giving the 1580 to 1640 for ethanol and 1750 for the keto group. Here we discuss the IR spectrum of aldehyde. IR spectrum of the different aldehyde, like the cyclohexenyl carbonyl aldehyde and ethyl 2-butanol, having the characteristic IR signature. We discuss about the IR spectrum of the carboxylic acid. You can see here the IR spectrum of the heptanoic acid, phenyl butyric acid, and cyclohexene carboxylic acid, and all are having different because of the different substitution and different types of stretching and bending vibration. We discuss about the benzene substitution pattern. For example, you can see here, if the benzene having the one substitution or attachment of the R group, it give you peak at the 750 and 700, but if it is the two substitution, it giving the band at 750. Similarly, if it is the band is shifted to ortho to para position, then it having the different intensity, and it is the ortho to meta position and ortho to para position, it give you the different frequency. And these are the list of the frequency observed at the different substitution of the benzene. Out of plane bending combination are quite small, but it is normally clean region of the IR, reliable even with nitro or carboxylic acid substitution. Here we discuss about the putting the sulfur silent and varying the different substituent. You can see here the RSH group having the absorption at 2580, but if it is the RSOR having 1050 per centimeter, if it is the triple substituted, then it is having the different, and these all are the details of the different types of possible substitution on the sulfur group at a center. Here we give a detailed discussion about the estimation of protein secondary structure using IR. So protein also giving a very good characteristic signature. You can see here in the figure that the IR absorption spectra of the protein, which give a peak at the 1650, and any conformation changes also causes a shift in the IR spectra of the protein. Not only this, the secondary structure element of the protein are also giving a characteristic feature, like for example alpha helix giving the amide bond at 3290 to 3300, amide 1 CO stretching gives the 1648 to 1660, and amide 2 NH deformation is collected at 1540 to 1550. Similarly, the beta sheet information can be taken from the IR spectrum and give the proper intensity at a frequency of 3280 to 3300, and amide 1 stretching at the 1625 to 1640, and amide 2 stretching at the 1520 to 1530. Similarly, beta turn, random coil, 310 helix, all these having a characteristic IR peak. We discuss here the IR spectra of the polynucleotide. You can see here the IR spectra of the polynucleotide, the guanosine monophosphate and DNA as a function of temperature. Not only this, you can also see the change on the temperature or change in the environmental factor also causes a dramatic change on the peak shifting, and that can be deduced by using IR spectroscopy. The IR spectra of the lipids, you can see here the representative Fourier transform IR spectra of lipid extracted from the rock catfish, that is giving a peak at 3800 and 800 centimeter region, and this is the IR spectra of the used oil sample having a characteristic peak at the different wave number. Here we discuss about the IR spectra of the carbohydrate. You can see here the FTR spectra of alpha D glucose and beta D glucose. Both are looking similar but having the different peak intensity. Similarly, wheat starch and microcrystalline cellulose. And this is the IR spectra of mixture of the plant materials like lignin, protein, and all these things. You can see having the different characteristic IR spectrum. This is the IR spectra of vitamins. You can see the IR spectra of alpha D tocopherol, then IR spectra of L-ascorbic acid, IR spectra of nicotinamide, and IR spectra of pristine. So these are the different types of IR spectra of the different vitamins. So students, let's now summarize that what we have learned in this module about IR spectroscopy, especially used for the biological molecules. So you can see here that especially for the different functional groups, so you can see here that the bonding RNCO double bond gives a strong peak at the 2250 to 2290 per centimeter. But if the oxygen is replaced by sulfur, like in the thiol group, then the showing a strong peak at 2000, in between 2000 to 2190 per centimeter. But if it is the all three nitrogen joined together by the double bond, a strong peak at 2100 to 2200 per centimeter was observed. But if you change in the other way around, like RCNNCR, then it gives a strong peak at 2150 per centimeter. However, in the case of cyanide, because of the presence of triple bond, it gives you a intense peak at 2250 per centimeter. But if it is the isocyanide, it gives you the strong peak at the 2130 to 2180 per centimeter. In the other case, if you have long chain of the alkene, especially known as allenes, it will give you a bond at a strong peak at the 1900 to 2000 centimeter. As far as we talks about the biological macromolecules, molecules also having different kinds of chemical component, and that's what you are getting as signature of the biological molecules in the form of, in the different form. For example, amide A band is appeared at 3300 per centimeter, and it is because of the NH stretching. And amide 2 bond in the protein because of the NH group, like the CN and CN stretching and NH deformation, it gives you an found in the spectral region of the 1550. As we talk about the lipid, it give you the, because of the CH2 symmetric deformation, it gives a peak at the 1470 centimeter. And amide 3 of the protein is because of coupled carbon hydrogen nitrogen hydrogen deformation, gives you an intense peak at 1290 per centimeter. If it talks about the DNA, RNA, phospholipid, in the case of nucleotides, there are OPO anti-symmetric stretch are there, and it will give you a spectral peak in the spectral region of the 1235. If it talks about the carbohydrate such as mucin, and also for the carbohydrate, in the carbohydrate, because of the carbon oxygen stretching, carbon oxygen hydrogen bending, peak at 1150 centimeter was observed. But if you talk about the DNA, RNA, and phospholipid, because of OPO symmetric stretching, an intense peak at 1120 per centimeter was observed. But in the case of phosphodiester group of the DNA and the RNA, the COP stretching gives you a band at 1070. But the disulfide bonds, because of sulfur bending, give an aspect found in the spectral region of 650 nanometer. This is a typical spectra which give you the information that what region of the wavelength gives absorbed light in the IR region at the for the different biological molecule. And you can see the lowest side is because of the amide bond of protein and then followed by the lipid, but in the middle part you can see it is because of the amide 2 and amide 3 band of the protein. Then you can see the band for the broad band for the fatty acid and amino acid in the, then you can see a broad band with the many soldiers for the nucleic acid, and then for you can for the find the bands for the phospholipids and other fatty acids. So this is the typical spectrum showing the IR absorption intensity at the different wavelength. Now we talk about the strength and limitation of this technique. Although this technique is a very widely used technique, but of course every technique have a lot of limitation. So in the first limitation, IR alone cannot determine the structure. For that you must have some other supporting data. The second, some signal may be ambiguous. Sometimes you may get the signal because of the other things, so that's what you have to be very careful, that the signal is whether it is due to the component or because of the some other thing. Then the functional groups are usually indicated. It's a good part, but the absence of signal is definite proof that the functional group is absent. So functional group presence may be overlaid, but if you are not getting a signal of the particular functional group, it means that functional group is at least not present in that molecules. And it corresponds with the known sample IR spectrum confirms the identity of the compound. So whatever the spectra you got, you must confirm with the compare with the IR spectra of the known compounds. IR spectrometry is applied to the qualitative and quantitative determination of molecular species of all types. This method provides a rapid and simple method for observing the functional group species present in an organic molecule. The quantum mechanical energy level observed in IR spectroscopy are those of the molecular vibration. And finally, it is the most widely used region of the IR is the mid-IR region that extends from 670 to the 4000 per centimeter. The near IR region lies from the 4000 to 14,000 per centimeter and also finds considerable use for routine quantitative determination. And the far IR region has been used for the determination of a structure of inorganic and metallic organic species. So now I hope you all must now aware with all the detailed information about the IR spectroscopy. Thank you.